What I want to talk about today is the history of the development of the atomic model, and this will be done in two videos, so in two parts. So the first person I want to start talking with is a person named Democritus. So his name was Democritus. He was a Greek philosopher, and he basically started the wheels, I guess, if you had to say, for the development of the atomic model. Mainly because what he thought was, well, if you were to cut something, so let's say I draw a little knife here. Oh, yikes. This. And let's say you had a ball and you kept cutting it, right? So you kept cutting it. Okay, now you have half a ball. Then you have another half of the ball, and then you keep cutting it. So now you get quarters, and you go so on and so on. You can represent it by some mathematical expression. You would reach something that cannot be cut. So you'd eventually reach, so if you kept on cutting it, something that cannot be divided. So something that's indivisible. So something that can not be divided anymore. And he called this indivisible thing, or I guess object, the atom. So he thought of this, which is pretty, that's quite profound, right? Like, I mean, to just think, oh yeah, so if you keep cutting something, eventually reach something that cannot be cut, right? That was his sort of idea. Then came another guy around the same time period in 400 BC. His name was Aristotle. He basically said, well, the elements that sort of make up this world are air, water, earth, and fire. So there was no mention of, atoms or all. It's just like, oh, the world, the universe is comprised of these four things. And well, while it sounds like, the plot from The Last Airbender, it's obviously not the case. That's not the basis upon which chemistry is developed. So in other words, he was wrong. So wrong. I'll just write that. No offense, Aristotle. And the reason, if you're wondering why his theory was accepted, because his theory was actually accepted for quite a long time. It was for two reasons. One reason being he was more popular. More popular than, I'm just going to say than Democritus. The other reason was his idea was more tangible. And what I mean by that is, if you try to think of something that you keep cutting on and on and on, eventually you can't cut it anymore. That's quite abstract to think about. It's a little hard to imagine. Whereas some guy just says, oh yeah, the world, the earth, whatever, is made of these things: air, water, earth, and fire. That's more tangible because you've seen these things or you've felt these things, right? So it's more tangible. It makes more sense to you in that case. So it was accepted for a really long time, like Aristotle's theory, over Democritus, even though Democritus was right. But that wasn't for too long, though, and that was when this guy came along, John Dalton. So he basically just regurgitated what Democritus said, and he came up with a thing: nothing is smaller than the atom. And his model for the atomic model is called the billiard ball model. And it's just basically a ball. Billiard ball model. So it's basically like this. And, you know, that's it. Shaded in, that's it. Nothing is smaller than that. And we know now from, you know, from our previous studies in chemistry that, well, there are things that are smaller than the atom. There are electrons, there's protons, there's neutrons. And if you want to take a nice dive into quantum mechanics, then you come up with even elementary particles that make up the proton and the neutron and so on. So the limitations are there for Democritus and John Dalton, even though they were correct. But it's definitely better than Aristotle. I think we can agree on that. Anyways, the next scientist, his name was J. Thomson. And so basically, he did some experiments with a cathode ray tube. And what he did was he passed a current through a gas, and he found rays of, I guess you could say, negatively charged particles. For negative, I'm just going to put the minus. And so what he proposed was that, well, his model is called the plum pudding model, by the way. What he proposes, well, the atom has something called the electron. And so basically inside, if this is my atom, there's this uniform, so there's this positive uniform charge. That's like the jelly. And then there's electrons scattered around here and there. So this was the first time we discovered something smaller than the atom. And it was pretty big. Even though the model itself was a little off, we know that the proton is in the center. It's still, you know, pretty good. And I'll write that down on the side here. Plum pudding model. So that was J.J. Thomson. The next person we have is Max Planck. So I'm just going to briefly summarize what his ideas were, mainly because I don't want to get too much into his experiments, because I feel like I'd be taking a nice deep dive into physics, and I want to try to keep this video as chemistry as I can. I don't want to scare some people or anything, but basically for a long time it was believed that light is continuous. And what I mean by that is that it has this continuous flow of energy, like a waterfall, for instance. Like a waterfall is continuous, right? It keeps going on. A waterfall doesn't come in chunks, right? If you think about it like that. So what he came up with through experiments, he did experiments with black bodies. Black bodies are just, you know, anything that can absorb and radiate electromagnetic radiation. But a black body is like an idealized body. So nothing is perfect, but like an example would be like the sun. So he did experiments with, well, not the sun, with, you know, objects like, let's say, pottery. And he basically came to the conclusion that light is discrete. Specifically, light has packets of energy, and it depends on its frequency. And he developed this equation where E for the photon. So energy of the photon equals to H, where H is Planck's constant. And F is the frequency. So basically, he came up with this idea that light has discrete packets of energy, and it can only dump or absorb the specific amount of energy. So these packets of energy that are discrete are called quanta. So basically he came to this conclusion based on his observations. His observations supported the idea that light is not continuous, that light has these discrete packets of energy, and it depends on your frequency. If you are aware of the electromagnetic spectrum, you know that things with a higher frequency, so a higher frequency equals, or not equals, I should just say proportional to more energy, right? And that's because their wavelength's a lot lower. So for example, UV is greater than infrared in terms of energy. And even though it's greater in terms of energy, it can only sort of disperse that energy entirely. It cannot disperse half of it or a quarter of it. It just dumps it all. That's how light works. So it's not like, it slowly trickles into something. It's not like a waterfall. It just dumps it all, moves on. So that's the idea. The light is discrete and it's packets of energy. It's like these little bursts, and it's called quanta. Now you may be wondering, okay, what the hell does it have to do with the atom? It's going to all shape up in just a bit. So the next scientist, just keep in mind what I said about Max Planck. So the next scientist is Albert Einstein. So you've probably heard of many of the things like he's contributed to, modern physics, like special relativity, general relativity, the idea that gravity is the curvature of space-time. We're not going to get into that. What we're going to talk about, his contribution to, I guess, chemistry, is his explanation of the photoelectric effect. So basically, for a while, this was sort of, it couldn't be explained. So let's say you had an electron here, right? There was this phenomenon where when you shine some light onto a metal, so let's say this is my piece of metal, and a metal has, electrons floating around. A metal has, delocalized electrons. And if you have this piece of metal and you shine a light on it, you would basically shoot off a photoelectron, which is just electron that now carries the energy of the photon. So photoelectron. And the explanation of it couldn't be done properly with classical mechanics. So what Albert Einstein did was, well, he basically took Max Planck's idea of quantum theory, of this idea that light has discrete energy. And he said, well, in order to shoot off this electron, in order to get this electron to just zing out like this, right? In order for this to happen, there's a certain frequency that must be met. There's a certain frequency because, remember, frequency is proportional to the energy, right? There's a certain, as can be seen in the equation that I showed right up here. This is so messy. Is that there needs to be a certain wavelength, a certain frequency that has enough energy to take this electron out of its place and shoot it up. So if you had, let's say, infrared, right? Not as much frequency, and it attacked this electron and it shot it off, right? Actually, it wouldn't. It probably wouldn't, because it doesn't carry enough energy. Because remember, something like UV, that looks like two V's, not UV. Something like UV has more energy because it has greater frequency than infrared. And so this photon here, it wouldn't be able to do it. It just wouldn't work. So big X. What would work is if, I'm going to draw this again. Here's my electron. What would work is if you, let's say, used UV light, something with greater energy, something that has greater frequency. And something with greater frequency, as you can see, it has a shorter wavelength. And eventually it would attack this, it would have enough energy, and it could expel this off. And there you have it. So this wouldn't work because infrared wouldn't have enough energy, but something like UV would, and it would be able to shoot off this electron, and now you have a photoelectron. So it couldn't be explained with classical idea, because people were a little confused. People just thought, oh, just increase the brightness of the light and then the electron will just shoot off. But that wasn't the case, right? It wasn't, the observations weren't matching. And Albert Einstein was able to explain this. It's just based off Max Planck's idea where, light has discrete amount of energy, and this infrared energy only has a discrete amount of energy that it can just dump at once. So you can shoot as many as you want. You can shoot as much infrared as you want. If it doesn't meet the minimum energy to take this electron out of place, it's not going to go anywhere. But all it takes is for one, light wave that has a great enough frequency to basically shoot off this electron out of place. So this is pretty profound. And, we're talking about electrons here, so this has something to do with the atoms. And we're going to see more and more of how this has to do with the atoms. And hopefully this all made sense. But if there's one takeaway you should really have is, because, from Democritus to J.J. Thomson and the other scientists you've seen, like Rutherford, Bohr, Chadwick, these are all the scientists you've seen in terms of the atomic model. But if there's one takeaway you can have is that Max Planck's quantum theory states that, and I'll rewrite it here, Max Planck's quantum theory. Is that light is discrete. Light has discrete packets of energy. And that's referred to as quanta. And that light can only dump that much energy. It can't donate like half of that energy or a quarter of it. It's sort of like money, right? You can have a quarter, 25 cents. You can have a dime, 10 cents. But you can't have a 35-cent coin. That does not exist, right? So that's basically it. And the other takeaway should be how Albert Einstein basically explained the photoelectric effect, which is just building upon Max Planck's idea of just quantized energy. So hopefully this helps. The next video, I'm going to be talking about these next 6 scientists and their incredible contribution to the development of the atomic model.